In this lesson, we're going to look at some of the basic properties, the basic ideas that are involved with quadratics. A quadratic function is a U-shaped curve, though it can be upside down. It could be stretched out. It could be really narrow, as long as it's a U, okay, not a V, not a two U's joined together. It's got to be a single U. This doesn't work. Okay, there's a couple of ways we can recognize things. Now, obviously, the picture is the easiest way, but we don't always want a picture or have time to make a picture. So the second thing we can do is look at tables of values. Tables of values is something we did in grade 9. We looked at our finite differences. This is the difference in your y values, only the y values. And we use little arrows. We'll do an example in a second, you can see. If you do your first differences, the difference in the y values, and you find that it's a constant value, the same number over and over and over again, well, that tells you it's linear. If it's not, you do your differences of your first differences. We call that the second differences. If those are the same, it's quadratic. And if your first and second differences are not the same, just stop. It's something else, something we're not sure about, some other kind of function. We're not really worried about what they're called for now. So, for example, let's say I have these two tables of values here, two different questions. I want to know if these are linear, quadratic, or neither. So I'm going to look at my y values and figure the difference between 10 and 20. Oh, I went up by 10. From 20 to 30, I went up by 10. From 30 to 40, up by 10. Those are all the same, and this is called my first difference, the first time I did this. So since they're all the same, we call that linear. It's a straight line if you were to graph it. If we try the second one, from 0 to 3, I went up 3, then I went up 5, and then I went up 7. Well, my first differences are not the same. So we do it again. We're going to call this the second difference. From 3 to 5, you have to go up 2. From 5 to 7, up 2. My second differences are a constant. That makes it a quadratic. If those weren't the same, you just stop there. You say, oh, they're not the same. It's something weird. Don't know what it is right now. Okay. Just be careful when you do your second differences. The sign of your second difference, in this case they're both positives, actually tells you which way the parabola opens. That is, positives open up. They make a happy face. They're very positive. So if you were not careful and you had minus signs there, it would actually tell you something completely different. You might think it actually opens down. And it's sad, it's frowny, down. Okay, so just be careful. Positive is up. Make sure you do your order correctly. Okay, so we can look at a picture, we can look at tables, we can look at equations. If I want to find a quadratic by looking at its equation, I have to examine the degree, which is the highest exponent of your equation after the brackets have been removed. When you have brackets, it makes it somewhat more complicated, so try and get rid of your brackets first. If your highest exponent is a 1, as in y equals mx plus b, the exponent on the x is a 1. That's a linear thing. If your degree is a 2, it's a quadratic thing. So for instance, y equals x squared. I see an exponent of 2, that's quadratic. Now you can have a mix of things like this, but remember we're looking for the highest exponent. Well, 2 is more than 1, which is more than no exponent at the end. The highest exponent is still 2. So if we examine the next example, which of these are linear, quadratic, or neither? I scan the first one for my exponents. I see the power of 2. That's a quadratic. In letter B, I scan it. I see a highest exponent of 1. In fact, I recognize this as mx plus b. That's linear. The third one, I don't see any exponents, but I do see brackets. We need to get rid of brackets. We have to expand first. So 5x times x makes 5x squared. 5x times 3 makes negative 15x. Look for exponents, a 1 or a 2. Well, 2 is higher, obviously. And since 2 is the highest exponent, that's a quadratic. In the third one, I see a power of 3. That's higher than anything we know about. So we call this neither. Okay, we only worry about ones and twos. Okay, so we have the graph, we have the table, we have the equation. So we're telling what things they are. Here's our key point for today. I want to recognize some of the properties of the quadratics. So there's a big list of properties. We'll go through them as we examine a single parabola, okay? A parabola is another name for a quadratic. We use those kind of interchangeably. So I'm going to go back and forth from this page to the next page, looking at an example and looking at the properties so we can identify what's going on here. So property A, the vertex, the point where the curve changes direction. So if I look at this example here, my curve is going up, 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 up until I get to here, then it's going down, 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 down. So we consider this point the vertex. We'll give it the letter V, and its coordinates are -2 and 4. That's my vertex. Okay. Letter B, next property, are x-intercepts, also known as the zeros. These are the points, and there could be more than one of them, where the curve crosses the x-axis. Okay, so if I look at my diagram here, this is my x-axis. I cross at that point right there. So I'm going to use the letter Z for 0, and that point is 1 and 0. There's another 0 farther over to the left. Again, the letter Z for 0 and 1, 2, 3, 4, 5, -5 and 0. Okay, you can have up to 2 x-intercepts, 2 zeros, so you don't have to. Okay, letter C, the y-intercept. We know what that is. We've dealt with that in the past. It's the point where the curve crosses the y-axis. You're only ever going to have one of those, and often it's not a nice point. This one's kind of nice. Our y-intercept is 0 and 3. But you often end up with decimals or really big or small numbers, so don't stress too much about the y-intercept. Okay, letter D. Letter D is a word, a maximum or a minimum. The question we ask ourselves is, does this graph have a highest or lowest value? Well, if I look at the graph and I think to myself it's going up and up and up and up and up until I get to the vertex and then back down again, I think of this as having a maximum. Okay? The graph is going to keep going down and down forever and ever and ever. It never reaches a minimum. It just goes and goes and goes and goes. But at some point, at the vertex in particular, I reach the maximum point. Okay, the axis of symmetry. Now this is a little tricky, this one. It's an imaginary line that divides our graph in half vertically. It has an equation, x equals. Okay, so I'm going to draw the axis of symmetry in here. It's the imaginary line goes right down the middle of the graph. Everything on either side of it is symmetrical. Because it's a vertical line, it's always x equals. If you look back at the property, it actually says it has the x value of the vertex. Right? The axis of symmetry travels through the vertex. So whatever the x is here, it's got to be the same x's all the way along. So our axis of symmetry, and be careful here, make sure it's an equation, x equals -2. Okay, letter F, the optimal value. This is the highest or lowest point that the curve reaches. It's the y-coordinate of the vertex. It kind of goes along with the word maximum or minimum. So for this graph, our optimal value, and we just write it down this way, okay, optimal value. We'd say this has an optimal of, what's the highest or lowest value I reach? I reach a maximum of 4, the y part of the vertex. So if you stop and think for just a second, the axis of symmetry and the optimal actually comes from the vertex, or the vertex comes from the axis and the optimal. There's a big connection there between those three things. We'll try letter G, the direction of opening, the direction in which the curve gets wider. If we look at ours, our curve seems to be getting wider as it goes downwards. So we would say this thing opens down. Okay, it's getting wider and wider as it goes down. You might think of it as the word concave down too, if you think about science. Concave down, opens down, same thing. And the last one, our second differences. We've talked about those already.
Dallas, please call extension 4503. Dallas, extension 4503.
Our second difference is the table. I don't actually have the table, but I don't need it. The idea with second differences is if we know which way it opens, we actually know what kind of second differences we have based on the sign. So opens up as positive, opens down as negative. We take a look at our graph, and what do we notice? We notice our graph is opening down. Well, that tells me that we have negative second differences. Okay, and there's one more connection here we're going to talk about. So if you know second differences, which we do, and you then know that it opens down. If you know it opens down, you then know it has a maximum. They have to go together. Maximum means down, down means negative. Okay, so if you know any of these three things here, you actually know the other two. Okay, see if you can try the next graph to label and or write down the 8 different properties of our quadratic. Okay, so we're going to write down our vertex. The vertex is right here, 0, -1. Our zeros, they're these two spots, 1, 0, -1, 0. Our y-intercept.
Mrs. Piper, please call extension 4503.
Our y-intercept, we actually happen to write down already. It happens to be the same as the vertex. That's allowed, nothing wrong with that. Okay, does this thing have a maximum or a minimum? Well, it has a minimum, it has a lowest point. What is the minimum? The minimum is an optimal of -1. When does that happen? When we have an axis of symmetry of x equals 0. And remember again, these two things come from your vertex. Because that has a minimum, we know that it has to open up, which you can also tell from looking at the picture. If it opens up, it has to have positive second differences. And again, we have the connection between these ones. Okay, there's our properties, our big 8. We're going to spend the rest of the course actually dealing with these 8 on an everyday basis, just doing different things with them. Okay, a little bit of problem solving just to finish this off. So the x-intercepts, the zeros in other words, of a quadratic relation are -2 and 6. The second differences are positive. Well, what does that tell us? That tells me if I draw this out, I know I cross the x at -2 and 6. If my second differences are positive, that tells me it opens up. So I know I'm going to have a rough shape like this. Okay? Sometimes it really helps to draw a picture to get things clear in your mind of what's going on. Hey, part A says, which way does it open? Well, my picture, it opens up. I also knew that because it had positive second differences. Hey, part B, is the optimal value positive or negative? Well, an optimal value is the highest or lowest value you ever reach. It's the y part of the vertex. That's down here. That's in the negatives. So my answer must be negative. What is the axis of symmetry? Now this is a key one. Something cool about the axis of symmetry. Remember our idea that this graph is symmetrical? Well, this distance has to equal this distance all the time. So if I want to figure out an axis of symmetry, I can take my two zeros and find their midpoint. In other words, add them together and divide by 2. If I do that, I get 4/2, which is just 2. I know my axis is symmetry. It's always halfway between the two zeros. And that's, again, a key point. Okay, try the last one yourself. See if you can figure it out, what's going on here. Pause it and see if you get it right. The zeros of a parabola are 3 and 5. 3, 5. The maximum, what does that tell me? Maximum happens when I do this, right? Okay, so it has to go like that, is 7. That has to be my optimal. The highest value I ever reach is 7. It's got to be something and 7. That's how high that is, right? 7. What do we need to know? Oh, which way does it open? Well, my picture says opens down. I also know because it has a maximum. The vertex. The vertex is my axis of symmetry and my max value. If I want to find an axis of symmetry, we just said that you should be able to add your zeros and divide by 2. So 8 over 2 is 4. Here's my axis of symmetry. So what's my vertex? 4 and 7. In part C, will the y-intercept be positive or negative? Well, I can't see the y-intercept on my graph yet. If I extend my line and extend and extend and extend, eventually it's going to cross the y, right? Way down here somewhere. Well, it doesn't matter what the number is. Either way, it's going to be negative. Okay? It all came about because my diagram helped me figure some things out. I'm not saying you have to draw a diagram, but it might be helpful to draw a diagram. Okay, and there's some questions you should try. They're pretty quick, but it gives you some introduction to the basics of quadratics.